I am too smart. I am too smart. S-M-R-T. I mean S-M-A-R-T.
All right, let me welcome everybody to the notes on 5-2. I will tell you this, you are going to be glad you are watching. There is a lot that goes on in 5.2, just as far as vocab and understanding these polynomial functions that we're going to be looking at, how to write them, analyzing them in factored form. So just lots of stuff going on. This is a really good unit. It's a really important unit to watch and understand. So here we go. So first, understanding the essential understanding down here is that the zeros of a function will help us factor it, graph it, and solve it. So understanding what zeros are. In chapter 4, we solved quadratic equations that looked like this, that were in standard form like this by factoring, and we wrote them out as linear factors in the form of x minus some number and x minus some other number. And then we applied the zero product property to solutions. We can solve polynomial equations the same, very similarly, okay, very similarly. So let's take a look here. We need to be able to factor these polynomial functions. So the first thing we want to do is make sure that we know how to factor. So just looking at this one, we're going to factor out an x. I notice that there's an x as the greatest common factor, and then we're going to factor that, and so we end up with this right here, so 3 factors. And in a minute we'll talk about how we can use that, but first we got to make sure we can do that. So go ahead and pause the video here. Nice little warm-up, breaking into this new difficult unit, making sure that we know how to factor polynomials. So find the greatest common factor, get that out of there, and then factor the quadratic that's left. Go ahead and pause the video and do that now. Alright, you've unpaused. Hopefully you got x times x minus 4 times x plus 3. Now if you have the x plus 3 and the x minus 4 in a different order, no big deal. That's no problem. If you don't have those, then that is a big deal. Alright, so that's that in factored form. So the key concepts, the roots, zeros, x-intercepts, all that stuff. So the following are equivalent statements about a real number b and a polynomial. So we're talking about this polynomial here. So x minus b is a linear factor of the polynomial. So we're just saying that if we were to factor some polynomial and x minus b was one of the factors, b is a zero of that function, b is a root or solution of that equation, and b is an x-intercept of the graph. This is the same thing we talked about earlier this year where x-intercepts, roots, zeros, solutions, those are all the same thing. They all are synonyms, okay? So let's take a look here. What are the zeros of this function? And then graph the function. So what are the zeros of that function and then graph the function? Well, to start that, we just look at each linear factor. So we look at each one of these and we apply the zero product property right here. So the zeros are -2, 1, and 3 because that's what would make each of these equal to 0 because of the zero product property. So then find the points for x values between the zeros. So if we have x plus 2, x minus 1, x minus 3, so we're going to find what is x when x is -1 or 0 or 2. So just some numbers in between those roots, okay? We evaluate and we get some points. We determine the end behavior based on what we did in 5-1. So this is x cubed, so the coefficient of x is positive, and it's an odd function, so we know it's down, up. We use the zeros, the additional points, the end behavior to sketch it. Now, is this going to be exactly perfect? No, but our sketch is going to be pretty good, okay? So let's take a look at got it 2, and we'll work on that one together. So let me throw a graph on here. All right, so there's our graph. So first we look at this. What are the zeros of this function? Well, we have x minus 3, and we have x plus 5. So the zeros, x equals 0, 3, and -5. So the first thing I'm going to do is I'm going to put points at 0, 3, and -5. Okay? The next thing I'm going to do is I'm going to find some numbers in between there. So I'm just going to pick them randomly, and then I'm going to substitute in and get some numbers out. So let's pick some numbers. Let's pick -3 looks like a good number to pick. Let's pick 1, and then let's just pick just for fun here. Sorry about that. Let's pick negative 3, 1, and let's just go ahead and pick 4. We'll pick those. We substitute those in and get some numbers out. So we have y equals negative 3 times negative 3 minus 3 times negative 3 plus 5. Okay. So we're looking for just new x value or new y values when x is one of these numbers. Then we have y equals 1 times 1 minus 3 times 1 plus 5. And then we have y equals 4 times 4 minus 3 times 4 plus 5. Okay, and when you do this, you might find, and we're going to find when we do this, that some of these numbers are way too big or way too small, so then you adjust your numbers based on what you get. So this is negative 3 times, well, this is negative 6, so negative 3 times negative 6 times 2. So that's 18 times 2, so this is 36, okay? So big numbers here. So we might adjust what our values are. Then this is 1 times negative 2 times 6, well 1, negative 2, 6, that's negative 12, and then this is 4 times 1 times 9, so this is 36. So we got some huge numbers, okay? So these are going to go way off this graph unless we say that each one of these is worth like 5. So we'll just do that. We'll just say that these are, or actually these are multiples of 6, so we'll just make that easier. So this is 6, 12, 18, 24, 30, 36, okay? And then these are just still 1s and 2s and 3s. So let's go negative 3, that gave us 36. So negative 3 and then 36 was all the way up here, so there's a point. 1 gave us negative 12, so that would be down 2. And then 4 gave us positive 36, so again, that's all the way up here. So there's that part taken care of. So now we have some points so we can make some sort of curve. Now what we need to do is we need to have an idea of what the end behavior is, and we also need to know what whether it's positive or negative, or sorry, that's end behavior. And then we also want to know, does it is it upside down or not? So what we want to do is let's take a look at the original function. So it's cubic, so x times x times x gives us x cubed, and none of the x's are going to be negative. So because of that, it's going to be shaped just like this one was. It's going to have a down-up end behavior. Okay. So here's where we get to just, you're going to sketch this the best you can. You know, you don't want it to look ridiculous, and at the same time, you're probably not going to be able to do it perfectly. So you just draw these out the best you can, using the points that you're given. So something like this. And it's going to turn there. And it's going to turn there. And there we go. So something like that. Doesn't have to be perfect, but it should look something like that. Okay? And that's how we can draw a function based on the given information. All right? The expression x minus a is a factor of a polynomial if and only if the value a is a 0 of the related polynomial function. So writing a polynomial function from its zeros. So what is a cubic polynomial function in standard form with these zeros? So now I'm giving you some zeros and having you write a function that fits that. Okay, that's all we're saying. So if negative 2, 2, and 3 are all zeros, then I can assume that these are now linear factors. I can multiply those out using FOIL. I can multiply again using the distributive property. I combine all my like terms, and then I can say this function, goodness gracious, this function right here is a cubic function that has those zeros. Okay? A quartic function with these zeros, I would do the same exact steps. I would multiply everything out. I would combine like terms, and then I'd get that. Graph both functions. How do the graphs differ? How are they similar? So then we just got to look at it and see, like, you know, how are they differ? How are they differ? How do they differ? Well, let's see. They both graphs have x-intercepts at negative 2, 2, and 3. That's one way that they're different. The cubic has down and up end behavior. The quartic has up and up end behavior. So they have, while having the same zeros, there's a slight difference in there that we'll get to in a second. The cubic function has 2 turning points and it crosses the x-axis at negative 2. The quartic function touches the x-axis at negative 2 but does not cross it. And the quartic function has 3 turning points. So a lot of information there. Let's take a look at this. What is the quadratic polynomial function with zeros 3 and negative 3? What's a cubic function with 3, 3, and negative 3? graph both functions. How do they differ? How are they similar? Let's go ahead and you try that one on your own. This is stuff that you can do. Follow these steps up here where we're just going to rewrite these and then multiply them out, combine like terms, get our two functions. Then you can graph them in your calculator and tell me some differences. So go ahead and pause the video now. When you unpause, I'll have the answers up so you can check your answers. Go ahead and pause the video now. Alright, so you've unpaused. I don't have the answers up, I lied. The answer to part A, so that's just x squared minus 9. And really, to be honest, and we should start, I should help you focus on this. It says graph the function, so we'll put it in function notation. F of x equals x squared minus 9. For part B, I just choose a different letter. G of x equals x cubed minus 3x squared minus 9x plus 27. Okay. For part C, you graphed them in your graphing calculator. Hopefully what you got is that they both have intercepts. They both have intercepts at 3 and negative 3. The quadratic function has up, up. So quad function is up, up. And the cubic function, hopefully you got that one, has down, up. You might have also talked about turning points, stuff like that. So that's good. You know, the quadratic has 1, the cubic has 2, 1 turn, 2 turn. Okay. If you had trouble with that one, that's not that easy of a problem to work your way through. There's a lot of simple mistakes that exist there. So if that's something you got wrong, make sure you make note of that so we can talk about it in class. All right. So we can write polynomial functions like problem 3 in factored form as this right here and this right here. And g of x, the repeated linear factor right here. So this is a repeated factor, x plus 2 squared. So that's called it has a multiple 0. Okay, it makes negative 2 a multiple 0. So all that, and we're going to talk about what that means. In particular, since the linear factor x plus 2 appears twice, we can say that negative 2 is a 0 of multiplicity 2. Okay, in general, a is a 0 of multiplicity n means that x minus a appears n times as a factor. So all that means is that if this is a 2, then it has a multiplicity of 2. If this is a 3, it has a multiplicity of 3. And so on. So we'll look at how multiple zeros affect a graph. So this is a big deal. If a 0 of multiplicity n in the polynomial function y equals p of x, then the behavior of the graph at the x-intercept a will close to linear if n equals 1, close to quadratic if n equals 2, close to cubic if n equals 3, and so on. So here's what that looks like. Okay. Finding the multiplicity of a 0. What are the zeros of this function right here? And then what are their multiplicities? And how does the graph behave at these zeros? So first we factor, and we get x squared, because we can factor out an x squared, x plus 2, and x minus 4. So then we just factored that. So what that means is you'll notice that the red part, okay, that's the actual graph of this function. Okay? If we look closer at the x-intercepts, since x squared equals x minus 0 squared, then the number 0 has a multiplicity of 2. Okay? The numbers negative 2 and 4 have multiplicities of 1. So what that means is that on the zeros that have a multiplicity of 1, the function just goes straight through it just like a line would. Okay? When it has a multiplicity of 2, it's going to touch that 0 and turn the other direction. Instead of going through it like it usually does, it's going to touch it and turn the other direction. Okay? It's just going to touch it and turn the other direction. If it has a multiplicity of 3, well, then that's a little bit. It touches it and sort of flattens out and goes through it. But that is not what this one did. Okay? It's got a multiplicity of 2, so it touches it and goes through it. All right? So let's take a look here. What are the zeros of f of x equals x cubed minus 4x squared plus 4x? So first let's graph that. Okay? So let's factor that. So we have x, we can factor out that, x squared minus 4x plus 4. And then you might notice that that is a perfect square trinomial. So this is x times x minus 2 squared. Okay? So what are the zeros? So the zeros are 0 and 2. Okay, that's the 0. 0 and 2. The 0 has a multiplicity of 1. 0. And here, because of the squared, the 2 has a multiplicity of 2. Okay? Very simple. If we're looking at multiplicity, so it looks closer to a quadratic. That's the point they were making up here. Because this right here was a multiplicity of 2, that part just looks like a quadratic. Okay? More vocab that we need to understand. We have these relative maximums and relative minimums. If the graph of a polynomial function has several turning points, it can have relative maximums. So it's not going to have a max because this goes forever up and forever down. But based on its turning points, it can have a relative max or a relative min, depending on where the turns are. Okay. So let's take a look here. What is the relative maximum and relative minimum of x cubed plus 3x squared minus 24x? So we can use a graphing calculator to find relative maximum and relative minimum. So just like they did here, they put the graph in, and then I don't know why the book loves using these tables. I put it in my graphing calculator here. I go to draw. Now I did play with the view window a lot, so you're going to have to know how to do that. Then I just go to GSolver, I hit maximum, and it's going to tell me the maximum is at negative 480. And then if I go to the minimum, GSolver minimum, it's going to tell me that the minimum is at negative 28. Okay, so putting this in your calculator is really no problem. Go ahead and do that for number 5. Put that in your graphing calculator and calculate the max and min for me. Pause the video now. All right, you've unpaused. Hopefully you got something like this. For the relative max, okay, for the relative max, I got negative 0.86 and 3.13. For the minimum, I got 0.64 and negative 2. Okay, something like that. So that's just a graphing calculator question. Using a polynomial function to maximize volume. Okay, to maximize volume. The design of a digital box camera maximizes the volume while keeping the sum of the dimensions at 6 inches. If the length must be 1.5 times the height, what should each dimension be? So we have x equals the length. We can determine the length and the width. So we got to know volume is 3 things, right? So the length is 1.5x. The width is 6 minus x plus 1.5x. So this is what we have. We have one of the dimensions. The sum of them has to be 6, right? So the sum is 6. We have x is the height. We have length is 1.5x, and then we have width equals however much is left. 6 minus the length and the height. Okay, so that's how much is left. We multiply that all out, and we get this cubic function. We graph it, and we use the maximum to find the maximum volume is 7.68 for a height of 1.6 inches, and then we can just plug that, use those numbers, find everything we have left, and then figure out what the dimensions of the camera should be. Not really that complicated once you get past the setup of all of the length times width times height. That is the hard part, okay? Now we're going to take the same thing though. What is the maximum volume of the camera in problem 6 if the sum of the dimensions is at most 4 inches? So all you're doing is you're taking the same exact numbers, except for you're going to change this 6 to a 4. Go ahead and change that 6 to a 4, do the same exact work, and come up with the answers for the length, width, and height. Pause the video right now and tell me what's the sum of the dimensions, what's the maximum volume if the sum of the dimensions is at most 4 inches. This is a calculator question. Change the 6 to a 4, and then find the max. Go ahead and do that now. All right, hopefully for this you got the maximum volume is 2.28, and that's inches cubed. If you didn't get that, make a note of it or try it again, because again, all you're doing is changing this 6 right here to a 4 and then graphing the max. You do have to find this. That'll be different, okay? So maybe you didn't do that. Try that. That's it for the notes. These are complicated, so do me a favor. Spread the word to people that you know that are in class that need to watch these notes. There's a lot of stuff going on here. People are going to have a lot of questions if they don't watch this video. Thanks a lot. I will see you nerds next time. Bye.